Hi everyone, welcome to another Doug's Lab video. In this video, we'll be synthesizing iron oxalate, as well as demonstrating the pyrophoric properties of iron. Now, this is a block of iron, and as you can see, it's reacting with the air. Now, pyrophoricity, or that is to say, if something is pyrophoric, it means that it reacts with air to combust spontaneously. So, when it's exposed to air, it'll self-ignite. Now, as you can see, this block of iron doesn't self-ignite in air. However, it is reacting with air. It is making iron oxide. Now, the interesting thing is, the finer we divide the iron, the more reactive with air it'll be. For instance, if I heat up this iron slightly, you can see that it readily reacts with air to form iron oxide. In essence, it's burning. But it's still not finely divided enough to become pyrophoric. So we need to divide the iron further. Now, this can't be done with mechanical means, because if you do that, the chunks end up being too big, and then once you start getting small enough chunks to spontaneously ignite, they do so. And that can be seen when you're grinding like metal parts. You see little sparks flying off. And that's partially due to heat caused by friction, and partially because the particles are so small that they spontaneously react with air. But not all is lost, because we can in fact synthesize fine enough iron powder to ignite in air. We can do it chemically. And so in this video, I will show you how to do that. Okay, so for this experiment, we need a chemical reaction that produces iron metal. In a chemical reaction producing iron metal will typically produce iron metal very, very finely divided in a spongy sort of state, which is perfect for demonstrating the pyrophoricity of iron. It'll be finely divided enough to spontaneously combust in air. So iron oxalate, the thermal decomposition of iron oxalate, is a perfect candidate for this reaction, because what we can do is take iron oxalate and heat it up, where it will give off iron metal and 2 moles of carbon dioxide. And as you can see, the oxalate anion is essentially 2 carbon dioxide molecules that are attached back to back. So anyway, how do we make iron oxalate? Well, we're going to need oxalic acid to do that, so you might want to order some oxalic acid if you want to attempt this. But and an iron 2 salt, because oxalic acid is -2 and iron is +2, and also +3. But we need iron +2 in order to make iron oxalate, and we need it in solution. So we need a water-soluble iron +2 salt. And for this demonstration, we're going to be using ferrous chloride, because it's easy to produce from common household chemicals. You're going to need hydrogen chloride, preferably in water solution. That's how it's sold, as hydrochloric acid. And you're going to need iron metal. And this is easy. We're going to use just hardware store hydrochloric acid and some steel wool to represent the iron metal. And this will react to form ferrous chloride. Not ferric chloride, that's FeCl3. And I'll do a video on how to make both of those coming up in the season. But we're going to make ferrous chloride, FeCl2, which is Fe+2 and 2Cl-1. So we now have our iron +2 salt in solution once we dissolve the ferrous chloride in water. So we have Fe+2. And we're going to add that to, in fact, let's do this. Ferrous chloride plus oxalic acid is going to yield us iron oxalate. And what's left? 2 hydrogens and 2 chlorines. So we are going to yield hydrochloric acid. And that's about it. So that's what we're going to do. We're going to take some iron, react it with hydrochloric acid, get the ferrous chloride, react it with oxalic acid to produce iron oxalate, which is not very soluble, and we can filter it out. And then we can thermally decompose the iron oxalate to form our finely divided iron, carbon dioxide, or then we can react the finely divided iron with air, or we can expose it to air to see if it burns. Alright, let's go to the lab and see if we can do that. Okay, so first step is to synthesize the ferrous chloride, and this is done by reacting iron with hydrochloric acid. Now I have 31.45% hydrochloric acid in this beaker. I have 30 milliliters of it in there, and this is stoichiometric with, well, it's actually slightly in excess of stoichiometric, which is good because it doesn't really affect the reaction, of dissolving 5 grams of iron in the form of steel wool to form hydrogen gas, and of course our ferrous chloride. So we drop this in, and you can immediately see and hear some fizzing. And then we can use this rod to push it down to get the reaction going very fast. Now, be careful when you do this, because the reaction is exothermic. It will heat the hydrogen chloride gas, or it will heat the hydrochloric acid up and liberate hydrogen chloride gas, which, as you can see, is fuming out of the beaker right now. And up into my convenient suction tube. So unless you have a suction tube, I would advise doing this outside, because hydrogen chloride vapors are extremely corrosive, and everything in your lab is going to start rusting very quickly. And also it's bad for your health, so don't do it. So anyway, I'm going to cut the video and come back once all of the iron has been dissolved, and then I'll show you how to process it. Alright, so here we have the solution of now ferrous chloride and a little bit of excess HCl. And I've added some water to it to dilute things down a little bit so you can kind of see it. But anyway, you can see it's kind of a black sludgy material because that's suspended carbon, because obviously the steel wool is not pure iron, it's steel, and steel is iron and carbon. And since we've dissolved away all the iron, what's left is a very fine suspension of carbon particles. And this will be filtered out to leave us with a green solution of ferrous chloride. So I've set up here for vacuum filtration, and I'm using vacuum filtration because it's much faster to filter out suspended particles like this. You could probably use a coffee filter, but it's just going to take you a lot longer. So I'll start my vacuum pump, and my vacuum pump, by the way, is just an old refrigerator compressor, and I'll give you tips about taking care of those in a later video as well. But anyway, so here we have the Buchner funnel and a 1 liter filter flask. Could be a lot smaller, but that's all I have. And we are just going to filter this to get our ferrous chloride. This goes in here. I'm going to get a little bit of water to wash out this beaker. Stir it around a little bit. Okay. And you can see we have filtrate coming out. Now we'll lower the tripod, which is noisy as hell. Okay, so we have filtrate coming through. Should be bright green ferrous chloride. I'm going to start the vacuum by seating this Buchner funnel. There we go. Now it's fairly dilute, so you won't be able to see much color. Okay, and as you can see, the carbon is being easily filtered out. And down here we have a slightly green colored solution of ferrous chloride. I'm just going to hold this down. So my little rubber filter aid is really hard, and it doesn't work very well unless you press on it really hard and get a good vacuum in there first. So I'm going to attempt to do that right now. It'll stay, but you just have to initiate it. And it's hard to do when the flask is mostly empty because it takes a while for the vacuum to pump it down. Or for the vacuum pump to pump it down. Here we go. Oops, no, a little bit more. Doesn't matter, it's almost all filtered off anyway. There, now it stays. So of course you can see the carbon being filtered out and any excess steel wool. Which you can see there's only a tiny little bit, which is not much, that's less than a gram easily. So there we go. Carbon has now been filtered out. And we have a slightly green solution of ferrous chloride. Alright, now we need to make our iron oxalate. And that is made, of course, as we learned earlier, from the ferrous chloride and oxalic acid. So, I'm going to break the vacuum here. Set the filter funnel aside. You can see the carbon that's built up in there. Take the vacuum. Alright, so we have our ferrous chloride. And we also have here 10 grams of oxalic acid. And this is right around the stoichiometric amount. I did the math, and of course we have excess HCl. The whole thing is a little off of stoichiometry, but 10 grams of oxalic acid will do the trick. And this needs to be dissolved in water. So I'm going to go add some hot water to this. Now, of course, if you were doing this analytically, you wouldn't use tap water, but we're just making something that we're basically going to burn, so I'm not using distilled water or anything. Anyway, so here's the water added to the oxalic acid, which I'm going to stir. And we better make sure the oxalic acid is completely dissolved. Now, iron oxalate has almost no appreciable solubility in water, so it should precipitate as a yellow precipitate, a bright yellow precipitate, when we add our ferrous chloride. So, here here's our ferrous chloride, and here's our oxalic acid. And I'm going to pour them together in a separate container. I'll use this beaker, but I'll just rinse it really fast. Okay, so here I got this beaker, and we're going to pour our ferrous chloride into it. It's a pale blue, kind of green solution. And if we leave our ferrous chloride out, it will actually oxidize to ferric chloride in the presence of air and iron, so it'll turn like a sludgy, nasty brown. So anyway, ferrous chloride, oxalic acid, mix the two to form bright yellow iron oxalate. And that's going to take a second to react, and then iron oxalate should precipitate from the solution. Okay, so here's experimentalism for you. Upon standing for several minutes, you can see that there's absolutely no precipitate forming. We just have a yellow solution. And my solubility data for iron oxalate says that it is less than 1,000th of a gram is soluble in water at 20 Celsius. So either my solubility data is inaccurate, or the hydrogen chloride that's left in solution, or the hydrogen chloride that's produced during the reaction, is keeping it in solution for some reason. I'm not really sure which one this is, but what I'm going to attempt to do now is heat this up to drive off the hydrogen chloride gas by boiling, and then hopefully precipitate our iron oxalate. So hot plate, turn it on high, solution on top, and I'll begin boiling this, and then I will take video as soon as it is boiling, and then we might be able to see it precipitate for me. Okay, so here's an update. You'll notice that upon heating, the solution is gradually getting cloudier. You see, you almost can't see my hand through it anymore. And I'm thinking that maybe the reaction isn't as spontaneous as I once thought, and that even just a little bit of heating will precipitate our iron oxalate. And as you can see, water is starting to boil off the hot plate underneath. So it's warming up. It's maybe 40 Celsius at this point. We should be driving off our hydrochloric acid anytime soon, which is of course going to make lots of fumes, so do this outside if you follow this method. And I will let you know how the precipitate comes out, if at all, which I hope it does, but it might not. So anyway, I'll have an update in a minute. Okay, so I've been heating it for about 15 minutes, and it has not reached boiling. I've been heating it fairly gently because I don't want to decompose my iron oxalate. And as you can clearly see, on the bottom we got this nice precipitate of iron oxalate forming. It's nice and yellow, just like it should be. So I think it might be time to filter it. Now, with continual heating, we might be able to get a little bit more out of it, and I'll experiment with this later. But in the interest of making the video in a reasonable amount of time, I'm going to go ahead and filter it. So I've already set up here for my vacuum filtration again, new filter paper and everything. We're going to turn on the vacuum pump with this plug. Okay, so the vacuum pump's on, and we're ready to filter. And we'll just take the hot acidic solution of oxalate, iron oxalate, and we'll pour it in here. Keep the rest on the hot plate. And through here we should be getting a perfectly clear solution if the reaction went to completion. And up here we'll be capturing our iron oxalate. Now I'm going to put the camera back on the tripod. And it's going to be super noisy, but I'm going to crank it up. Okay, so now you can see what's happening. And I'm simply just pulling the solution through. And yeah, I can press down on this to increase the vacuum, form a nice seal, and filter it better. And then the beaker, of course, we'll swish it around to get as much of that precipitate up as possible before pouring it in. And there we go. And as the solution cools, we'll probably get more oxalate precipitate out because, of course, the iron oxalate is going to be probably, well, as with any compound, is more soluble in hot water than it is in cold water. But that's something to keep in mind if you'd like to get a nice qualitative theoretical yield. Once again, pressing a little bit to get the vacuum going. And you see the solution in the bottom is slightly yellow, which is kind of concerning, meaning we probably don't have theoretical yield. But again, I'll keep heating that, and we'll see if we get any more precipitate out of that later. But you will notice that in the top, I now have a nice yellow cake of iron oxalate. So this method does in fact work, and in fact I scaled this up not too long ago, and over here I just so happen to have a big old batch of iron oxalate, which is now drying. And I took this whole video before, but I didn't like it, so I redid the whole thing. And this is basically the end of the part I needed to redo. And so I will, in a minute, or not for you in a couple of seconds, I'm going to play the videos where I use, I demonstrate the pyrophoric properties of iron by decomposing the oxalate in a test tube. So you can go check that out right now. Okay, so here is the final product. It's bright yellow solid. I haven't weighed it yet because it's still a bit damp, but I think we can do this experiment still while it's damp, and I will put the final weight in the description, along with the theoretical yield and whether that solution ever precipitated more or not. Anyway, I have a test tube and a propane torch, and we are going to torch the test tube full of iron oxalate to decompose the iron oxalate into CO2 and iron metal, which should hopefully be pyrophoric in air. It almost looks like it's boiling, but it's not. It's a powder. Oh, and my sock caught on fire. Anyway, we'll heat it until there's no more gas evolution. Okay, so now I'm going to go turn off the lights and dump this iron out onto the glass plate. And you should be able to see the pyrophoric properties of iron in the dark. Okay, here we go. Ooh, neat. So anyway, that was pyrophoric properties of iron. And yeah, I hope you enjoyed the video, and look forward to more videos coming this season in 2012. That's another Doug's Live video. Thanks for watching. Please subscribe, rate, and comment.